So now it's really started. Good morning, everyone, and welcome to this NISQ webinar. So I am Pascal Bernier-Brunner. I'm the dissemination leader for this research project. And today we are going to talk about quantum probabilistic safety assessment, QPSA, and our speaker, Mohamed Ibti, will give us a perspective within the NISQ era. So before we really go into today's subject, I would like to explain what those NISQ webinars are about, because this webinar is one of a series aimed at early users of quantum computing. So our objectives are to help the quantum computing community discover and test the libraries and tools we make available. Our objective is also to get your feedback. We are really interested to know what you think of what we've done. If you look at our publications, really give us your feedback. And so we're going to we have monthly webinars. We started actually in September. So past webinars have been recorded. You can access them through our website. The URL is here. And we have more webinars coming until the end of the project at the end of 2024. So we have, unfortunately, we had to delay a little bit the next two webinars, but in January, on the 23rd of January, we'll talk about benchmarking. We have a benchmark suite for quantum computing applications. And in February, we will talk about financial applications and especially about the Quantum Quantitative Finance Library. And registration is open for those two webinars. So really, if you're interested, feel free to register. And we have more coming, quantum natural language processing. This will be probably in April, but I'm waiting for a date, a precise date. And in March, we'll probably talk about chemistry. So, I mean, really stay tuned and follow us on LinkedIn if you want to have the news regularly. We are organizing webinars regularly. So let's get back to today's subject. If I can go to my next slide. So today's speaker is Dr. Mohamed Ibti. Hello, Mohamed. Mohamed is from EDF Research. And I'm not going to go through his whole bio, but he's the leader of the methodology and software support team for the PSA community at EDF. And he's been doing that for more than 10 years. And he has been involved in many research projects, and he's now in NISQ since the beginning, I think. I also wanted to highlight that there have been several publications concerning, related to today's topic. So I have put the list here. It was also on our website, and I think it was in the invitation. So don't hesitate to consult these, to check what we have done, check our open source libraries. This is a complement to what we are going to talk about today. So, Mohamed, the floor is yours. You can share your slides.
Thank you very much, Pascal. Thank you for this kind introduction. I will try to share my screen. Okay.
I'll tell you when it works.
Yeah.
Maybe I should stop sharing, or?
I don't know, but
I have stopped sharing.
It says it is loading.
Ah, okay. Yeah.
Okay.
Yeah, I can see your slide.
So, I would like to thank all the participants to this meeting. I would like to apologize for some of them who already have seen some of this work. Hi, Vishanti. So today I would like to talk about probabilistic safety assessment. And this is mainly what we use to assess safety for our nuclear power plants. And the plan I propose is to give you an introduction to risk assessment or to probabilistic safety assessment. What EDF expect in this initiative, or why EDF is trying to study quantum computing or to understand quantum computing. Then I would like to show you some very elementary work on PSA computation for our problems. And then I will talk a little bit about quantum approaches for sequence processing. So sequence processing is something we do to understand our failure scenarios. But for complexity issues, we do not use them because of the size of our systems. But now with quantum computing, we are trying to prepare this for the future. I will talk a little bit about hybrid approaches and finish with some conclusions and perspective. So before I start, I would like to recognize the contributions of many colleagues who worked with me in this project. Some of them, Francisco Siciliano is an intern at EDF at that in 2017, I guess. Ahmed Zayu did a PhD under the supervision of Professor Benani and Mr. Matei. So he already finished his PhD thesis on the topic, and he is the main contributor of a lot of the things we already did. David Herrera Marti is a colleague at that time in Atos. I guess he left Atos, but we did a joint work together on this topic. Sliman Thabit, Pedro Enrique Ponce Fioronta, and Arina Ivanova are students who did their internship at EDF, and they contributed to this effort of doing quantum computing at EDF for the PSA problems. Maybe I won't talk too much about Arina Ivanova, who tried to do some implementations of our problem into Pascal, but she also contributed to this project, and I would like to recognize their contributions to this topic. So what is PRA? PRA is probabilistic risk assessment or probabilistic safety assessment. It depends on the different wording in Europe or in USA. It consists of determining all the potential undesirable consequences associated to a system or to some process. And doing PSA is trying to identify all the ways such consequences could materialize, and not only identifying qualitatively what can combine or what can lead to some consequence, but also estimating their likelihood, which means that we are about estimating the frequency of having an undesired consequence or the probability of having such consequence. And the idea is to provide decision makers on optimal strategies to assess safety in different complex systems. So by the way, this methodology is not only in the nuclear power plant community, but also in many industries like transportation systems, like aeronautic systems, like oil and gas industries, like avionic systems, or in airplane safety. So this methodology is widely used, and now for our systems, or for some of these systems, we are starting to have some issues. So the main problems here are mainly related to reliability issues regarding the systems. And the main aspect we have is that we have systems that may be very complex in their properties, in their size, or the different dependencies they may have, but also in the properties that may emerge regarding some situations. So we are dealing mainly with SAT or all SAT. Given a Boolean formula on a set of variables, find all the evaluations on one evaluation if it is SAT that runs the formula through. And the idea is here to see what are the failure combinations that can sum it up to give, for instance, a failure of a plane, a failure of a power plant, or let's say a core melt in a power plant, or something like this. We, in addition to identifying the combination of these failures, we have also the idea of quantifying probabilistically what is the probability to have such combinations. Another problem is the problem of reachability. So given a finite state automation, identify all the transitions that lead to a failure state, starting from some safe state. We want to see if we can reach a failure state, and the idea is to identify all the sequences that goes through the safe state to the end states or to the failing states. And we have also to quantify these frequencies or these probabilities, and these are mainly the problems we deal with in our domain. Well, as you can see, these are complex problems. So if they are not NP hard, they are PSPAS hard. So let me show you how we formalize scenarios. So our scenarios are studied given some initiator. An initiator is something that push the system in a challenging situation. For instance, if we have a tsunami, or if we have a fire, we may have to handle this, and this pushes the system in a situation when we have to ensure that the safety functions are still met, and for this we highlight all the ways these safety functions may fail. So in this event sequence diagrams, I don't know if you see my cursor. Okay. If anyone
we do
can,
see your
can
cursor.
give
We
me
do
a
see your
feedback.
cursor.
Okay, thank you very much. So in this diagram, this in gray, these are safety functions, and the white small boxes represent systems that mitigate the effects of some initiator. Let's say, for instance, we have as initiator a fire in some location of the plant. So we need to see if we can maintain or if we can guarantee the main safety functions, which are the control of the power plant. In the first place, we have to ensure that the core won't melt. And we have three main functions that assure this. Here we have reactivity control. Here we have what we call the heat removal by different means. And here we have the maintaining the integrity of the nuclear building. So here, each function is applied when it works. So we have in green a success, and we continue applying all the safety functions that goes through all the safety functions here and go to some acceptable consequence. So here we maintain the safety of the plant. The other failures so we apply a number of additional systems. So we have redundancies. So this is just an example. So we apply the redundancies, and when we fail in the redundancies, we get to some undesired consequences that may be even being in the situation of another accident or damaging the core of the plant. So this summarizes all the initiator, all the scenarios that are triggered by some initiator. And the way we represent this is event trees. So this is a formalism that is considered by the industry to represent all these scenarios. At the end, these event trees are translated to fault trees, what we call master fault trees. And if we see these functions here, I can show you an example. So these are system failures. And system failures are studied here. For instance, if I have to supply water to some system here, so I have a software that helps me provide or generate all the fault trees that may explain the failure of the system I am applying to satisfy some function. And we get a fault trees, and this fault tree is integrated in this event tree. So these headers are fault trees, and we get at the end with some very big fault tree that we call the master fault tree for quantifying the kernel. So just to say that we end up with a very big fault tree, that is the master fault tree for each sequence. For instance, if I consider this sequence, so the master fault tree representing this sequence is something like this. When I have a big Boolean formula, it is random it's not random, but I mean, the distribution of gates and connectors is very random in the sense that they appear everywhere. And the idea is to try to find all the solutions or all the instantiations that may make this formula true. So the problem is, what we try to find is all the combinations that make this formula true, and we would like to write it as a disjunctive normal formula. So this first conjunction represents what we call a cut set. I mean, a cut in the sense that if we apply all these events, the top of this formula will become true. And we have disjunctions of this kind of conjunctions. And whenever we have one of this, we can make the formula true, and we can reach the undesired consequence. So the idea is to compute all the probabilities here and get the main probability here, the probability of having such formula, to have an idea of the probability of having some consequence. Classically, we have different algorithms that are used mainly. I'm talking only about what we use in our industry. So we have MOCUS and all its variants. So this classical class of algorithm deal mainly with approximation algorithms. So rewriting the for tree in such a way to get modularization. So the idea is to compress information and work with some formula over modularized cut sets. And then once we obtain the cut sets over modularized formula, we start generating all the detailed cut sets. So this is mainly used in commercial tools that we use in Europe or in everywhere in unless in some places people start using BDD algorithms. BDD algorithms work very well for small models, and the idea is to write the corresponding BDD to the Boolean formula and then trigger or generate all the cut sets and compute all the probabilities. The BDD algorithms and its variants, the ZBDD and all this stuff, work quite well for small models, but for some models, I mean, mainly the majority of the models we are dealing in the nuclear industry, it takes some days to build a BDD corresponding to some consequence. So this is the state of the art of classical algorithm. In the dynamic aspect, we sometimes want to credit the dynamic of the accident. I mean, we want to take care of the order of the events. We want to take care of normal and standby modes, which means that we want we want to consider some failures only where when the system started working or started functioning. We want to credit recoveries during mission times, and instead of having prime applicants or cut sets, the idea is to look for the sequences that may start from some initiator to and end in a consequence. So this gives you an idea of a system with two components. So when we start to model three components, we see that the number of sequences is increasing in an exponential manner. So the difficulties we have is that the size of our model, since we started to model seismic, fire events, tsunamis, a lot of external events, including flooding and so on, our model started to become very complex and big, and we are in the frontier of intractable problems, and we started to have very long computation times. So what we expect at EDF is at first preparing our institution or our company to understand what quantum computing can give us or can provide us. And in the static approach, we wanted to explore the algorithms that are already implemented or already identified, look for new algorithms, and explore ways to deal with uncertainties, explore other formulations for our problems. In the dynamic aspect, we wanted to explore different formalisms to see if the quantum computing can allow us to go further what we do in classical computing. So this is a map of the different routines we have seen, and that may be connected with the PSA problem. So we have seen Grover and Contine, Hamiltonian algorithms, quantum works, direct implementations and optimization, or going through ST networks to apply some of these routines. So just to give you an overview, so for SAT, all SAT, and for tree analysis, so we have a lot of similarities here, so we can use similar routines. And for the sequence processing, so we found out that quantum works could be a direction to follow in addition to quantum to hybrid quantum works. So and now I would like to give an introduction of what we already did. The first attempts we only try to see if we just cannot implement our formula in the form of quantum circuits, and it was very simple. The idea is to write the equivalent, the quantum equivalent of our gates in the fault trees and getting circuits that we can solve. So here we try to see if we could use ZX calculus and circuit optimization to simplify the formula we obtained and the circuit we obtained. And it turned out that it was not efficient. But this effort was not useless, because when we tried to identify the circuit optimization approaches, we found out that there were many approaches that can help optimize the circuits. For instance, manipulation of algebraic equation by Hutzel and Greenwood. All the ZX calculus formalities and libraries that were developed since 2014 by Duncan and Pedrix. Lazy synthesis, this is a very small non-exhaustive list, but there are many approaches that were developed to deal with optimization. But the main issue here is that these approaches helped us, or let's say pushes us to see what we can do classically. And one of the thing we have found out is that we can, when writing fault trees, we can identify patterns that may be much easily solved using, let's say, quantum oracles, or using either static classic solving. And the idea here is to try to rewrite fault trees. And the way we write our fault trees is an automatic generation using expert systems. But what we found out is that we can indeed manage the way we generate these fault trees, and keeping the same semantics or the same content of the fault tree, we can write these fault trees in such a way to have blocks or patterns that may be very quickly solved using quantum routines, or even either using classical algorithms. So this is a side effect of working on quantum computing for the classical side in our problem. Another attempt was that we tried to use Grover search. So with Grover search, we very quickly found out that we could write a circuit that use Grover search and find solutions for our Boolean formula. But here, the problem is that for small instances, somehow we know how many instances we have, and we can tune the algorithm to find, I mean, the number of Grover rotations, and we can very quickly solve this using Grover. But in real case instances, it's a little different, because we don't have any idea about the solutions or the number of solutions of our problems, and this is a main issue. So what we did, and we did this with David Herrera Marte, is to try to use counting in addition to Grover. And the idea is to use counting to find out the number of solutions, and then use Grover to solve the search problem. And it turned out that we have found another algorithm which is long algorithm that showed better results than counting plus Grover. It is 100%. I mean, the success outcome is guaranteed 100% when the Grover algorithm plus counting could not provide such success. Percentage. The issue with Grover in our problems is that we need a big machine to handle a significant number of quantum bits to deal with some real instances. After that, we tried to use an algorithm that was developed by Cheng and Tao. And this algorithm is a cooperative, let's say it's a hybrid algorithm. It's a cooperative search algorithm that use a mixed register, a classical register added to a quantum register. And the idea is to limit quantum actions to the very small quantum registers with the available number of quantum bits that we have. And we use the auxiliary classical register to prepare potential solutions or candidates for the Grover search. And this algorithm is based on some heuristic of choice of variables based on the minimum of appearance of the variables in the different blocks or in the different literals of the Boolean formula. So this algorithm, I mean, it turns out to be very efficient with a lot of codes. I mean, we found out that it guarantees some advantage. So if we take, for instance, a formula with 50 variables, and if we assume that the number of classical bits is the number of maximal number of the generations, that we can see that we can have something like 1,100 less queries than GenSat. And GenSat is the genetic algorithm that help or that solves SATs. So the idea is to get a number of queries over GenSat, and this algorithm, this cooperative algorithms, allows to lower this number of queries. Saying that, we don't know if this algorithm, I mean, this computational advantage, we are aware that it's not that advantage that can allow to consider that we have a speed up against classical algorithms, but it is a step to try to understand how we can use in nowadays hardware, how we can mix quantum algorithms and classical algorithms to go further and to try to do better than the classical algorithms. Another approach that we have tried to apply also is divide and quantum classes of algorithm. So our colleagues from Leiden introduced us to this methodology, and you have the works of Vedran Junko, In the NISQ project, we had a work by Renella and other colleagues from Leiden. In this framework, instead of considering a combination of classical and quantum bits, all variables are considered quantum, but formula are reduced by packaging them in small fragments, then quantum solved. And in this, maybe this is something you can find in the Git repository. So we have a library that do this. So this approach is quite ambitious in the sense that we need a little more qubits that than the computers we could work on. So we have two factors that must conspire. The search space must represent a tree with a decomposition into trees. This can give some quantum advantage. And this is unfortunately not always easy to have. The problem in our industry, at least, is that we have different systems that may have contributions for different kind of systems. Let's say we have electrical systems, cooling systems, and I and C systems, instrumentation and control systems that may provide something to different front-end systems, and this implies a lot of dependencies, and these dependencies may make difficult to get such conspiracy properties. So we did a small benchmark between the divide and quantum and the cooperative approach. So we adapted the cooperative approach to deal with some fault trees, and we have seen, and this is not a surprise in the sense that we could solve up to 10 formula with 7 nodes in the first approach with divide and quantum, but we couldn't go beyond. But with the cooperative search algorithm, we could go beyond very easily. But here, I just wanted to note that this cooperative approach is mainly using classical routines. So we cannot consider really that it is something, I mean, in this comparison, I would confess that we compared two things that maybe this is not a two compared approaches or comparable approaches, because we do not compare the same quantum aspects. Now we have another idea, or we had another idea of solving our fault trees, but here by translating our sequences not into fault trees, but into complex networks or into graphs. And in this framework, instead of, so for instance, if we have some sequence diagram like this, it's very easy to translate it using the very topology of the systems we deal with, and we can write some networks. The idea is that finding cut sets is the equivalent of finding vertex separators in graphs. And we recently, I mean, in 2017, there is another approach that starts from Boolean formula and write or translate the problem of solving Boolean formula to a problem of solving ST connectivity in a network. So this problem is quite the same. the main difference is that in this approach, we already have these topologies, because this comes from some real systems, and we can write very easily the topology of the complex networks. So in his PhD thesis, Ahmed Zayoub wrote an algorithm, a quantum algorithm that solves this problem by an oracle of movements. So using this oracle and superposition, we can move across the graph in a kind of superposition and get all the ket sets of our systems. So there is some equivalence between this problem and the problem of fault trees. The main difference is that in this framework, we have already a compression of our fault trees, in the sense that for the components we have here, for instance, we have a number of failure modes, which means that some nodes that are under some OR gates are already compression in one node. So this framework, in addition to be quite suitable for doing quantum circuits on it, is also something helpful to reduce the number of qubits needed to solve these instances. So for this approach, so the idea is to start this kind of oracles to move from a node to its successor and push the successors in the next ket sets. This approach is quite interesting, but to solve real instances, I mean, very big networks, we need a lot of qubits. Even if we do not, one thing with this approach is we do not need too much auxiliary qubits to find the different ket sets. Now, for quantum processing of sequences, as I showed you before, so we have a problematic to reach the failure states going from some safe states. One of the issues, or one of the challenges, is that how can we find all the possible states? And the second is, somehow when the system changes, how can we find the most probable scenarios from the new states pending the search for all possible scenarios? And how to compute the probabilities or the frequencies in this perspective. So the number of sequences is very high, because the size of the system state or the graph of the states of the system is progressing, or is scaling exponentially. So the idea was that we want to represent to have a superposition and represent these paths as superpositions of quantum states. So a path is represented by some state lambda, for instance, which represent a path from V1 to Vn. And we say that a vertex V is in the path if and only if the qubit Vi of the state lambda is in the state 1. So if I take this step, or this, I go through all the nodes here that are represented by 1 in this superposition of states. And here, as you can see, the problem is a problem of a number of nodes in the graph. So if we have n components, we have about 2 power n nodes, and this is a huge state. So there is a need of a lot of qubits. Another issue we have is that we wanted to credit, as I said before, we wanted to credit the loops. Loops here may represent recoveries. So for instance, if my system is going through some failure transitions, I want to some extent credit the recovery from this system to the initial state, or to say to the previous state. And to do this, we inserted or we introduced an additional node that help going from the current state to this virtual state, and then have other transitions from the virtual state to the next states of the very initial state from which these transitions happen. And the idea here is to break the loops and keep the different paths, even with transitions, to have only to deal with directed graphs to apply our quantum routing. So now the oracle is that we consider movements from each nodes to its successors, and then we add up, or we sum the different probabilities of the paths, or it's not a sum, it's a product, and then we can have the probability or the frequency of the current path. Now, this is a kind of let's say quantum walk, but with the idea of storing the probabilities and storing or computing the probabilities of the different paths along with the progressions of the graph. Now, there was different approaches we have tried regarding this problem, but at the very end we come up to compute the probabilities at the very end of the quantum process. And the idea is that it was very demanding to compute these probabilities. So the first algorithm is to collect the successors of any nodes of the graph to build the different sequences. In the quantum case, we use n qubits if the n is the number of nodes of the graph, and we use at most m quantum gates, where m is the number of arcs. So I have to speed up a little bit. This algorithm, however, as I said, we do not have sufficient number of qubits to apply this algorithm, but then hybrid approaches can play, and this is something we did. Ahmed have implemented this in his PhD thesis, and what we did is that we simulate this on quantum simulators and not on real hardware. So the idea of this hybrid approach is to recursively apply the algorithm we have seen before to subgraphs of successors. And the idea is to go recursively from one node to its successors and try to catch only a number of successors that we can do given the number of available qubits in the quantum hardware. Then the probability of the sequences is computed classically. We do not compute the probabilities quantumly. I mean, if you want details of these algorithms, there are some papers that have been published, at least in the NISQ project. And this hybrid algorithm were tested. So the idea is to start doing, given the number of available qubits, start going, collecting the successors. And then at each step, when we finish, we start by another routine. And one of the problems of this approach is we have no idea how in a real hardware this could apply, in the sense that by the way, in all these algorithms, we didn't implement the errors. We didn't inject or simulate having errors in the quantum operations. So this is the main oracle, and I need to finish. I see the time. So we did some results just to show you that in an IBM quantum simulator with 32 qubits, so by our approach, we could go far beyond what we can do. And from what we could solve in our systems, we could reach I mean, a number of seconds that we could not reach by classical algorithms. But at the end, we cannot verify this classically. So classically, we could not verify that these are all the solutions we should have when the instances become very important. So just to show you here the analysis of the running times of our approach. So our approach is in green here, so you can see the times here, and the number of paths found by here in different simulations, the number of paths we can find by quantum approach regarding the other solutions. Now, just to give you an idea of how this hybrid approach can be used, we did with Pedro Enrique another approach regarding the vertex separator problem. So we also implemented an approach when we could do this in a similar way. The idea is that from a big network, we can divide it, or we can divide the network in small parts that we can, for which we can compute cut sets, and then we assemble the main solutions within a very complete solution for the ST network. So in conclusions, different algorithms were tried for static and dynamic approaches in safety assessment. These algorithms are demanding, or qubit demanding, and it seems for us that hybrid approaches seems promising if we can guarantee that the hardware may help to do these approaches in the right way without a lot of errors. So I will stop here to let you ask some questions. I'm very sorry.
No, it's okay. It's okay.
So
yeah,
if you have any questions,
share my screen. So if you have questions, you can use the. Sorry, can you see my screen? Oh, but I'm trying. I was trying to.
I can see your screen.
Yeah, and it's not covered by. Yeah, but I'm trying to go into slideshow mode, and yeah, now. Okay, so if you have a question, you can raise your hand or enter it in the chat. Vicente, I see you have a question. You can raise your hand. Let me check. Normally it should work.
Hello, can you hear me?
Yes, yes, we can hear you.
Good morning, everyone. Thank you, Mohamed, for a wonderful presentation of your work. Probably I missed something, but I'm concerned about one thing. Is the causal relationships between events. I mean,
is the
causal relationships, causal dependencies. When in a problem like yours, in my opinion, so everything goes well if everything goes well, and everything goes bad if something goes bad. So the problem is that you are treating your problem, which is a very complicated problem, from in my opinion, from a very static viewpoint. How you manage the temporal dependencies between events? Because
this is a very good question. Yeah, I get you. This is a very good question. I mean, right now, we have a big assumption to have such formalism, and this big assumption is that we need all the events that we have in our for trees. I mean, the leaves should be independent, or at least they are assumed to be such. And one of the issues we have in our models is that sometimes we can have what we call some dependencies that are of different types. For instance, some dependencies are due to, let's say, design failures. So for some systems may fail at the same time because of the design. Some, then you have this kind of dependencies. So there are a lot of dependencies that we consider under the name of common cause failures. And we have a way to deal with this in a quite conservative manner, is that we can assume that a component may fail if it fails inherently from its own, or it fails because a dependency parameter, because of a common cause failure. And in this case, not only this component fails, but also other component may fail. But we can consider, for instance, if we have a redundancy between three components, we can say that these three components fail, and we have different probabilities for failing. We have a big probability for failing the component in an independent manner, another probability of failing the component A and B, and another probability of having all the three components failing for some hidden reason that we have because of the dependency. Now, this is something we consider very explicitly. The other side, and I agree with you, we may have the other conditions when we have what we call external hazards or internal hazards. By internal hazards and external hazards, we mean, for instance, flooding or fires or any other hazard that may impact the plant. And in this case, we have a methodology of doing this dependency assessment. For instance, we can consider that in a room, all the components that are in the same room may fail the same way because of some fire or because of some flooding, if they are not, for instance, above some altitude. So there are different ways of considering the dependencies. And the main issue is that we are conservative in our approach. And what we need to do, and this is a research axe, is to see how can we deal with the dependencies between the event, and then we won't be within the PSA framework. We need to go outside. I don't know if you answered your question.
Well, thank you, Mohammed. I think we've reached the end of our webinar. But thank you for this presentation. Did you want to add a last thing, Mohammed, or?
Well, since I see some colleagues here who participated to this project,
yes,
I would like to thank them very much for their helpful suggestions, Gonzalo, Andres, for their help during the NISQ project. And this is very nice to have them here.
Yeah,
yeah,
and the project is also about encouraging exchanges with people investigating completely different domains. So we see from your example that it works. So we've reached the end of our time, and I don't see any question in the chat. So I think we will close for now. Thank you very much for Mohammed for sharing your investigations. It was really interesting. And thank you everyone for attending this webinar, and I hope to talk to you again in January about our benchmarking suite, or in February for about our finance library. So thank you very much.
Thank you very much, Pascal.
Talk to you soon.
Thank you.
Bye.
Bye.